test method verification. We'll see why it's important to do TMV, okay? We'll also understand the TMV process flow from the beginning to the end. And also we'll get to know what are these studies that are being done under test method verification in our labs. So just to begin, from our introduction here, by definition, we need to know what is verification and what is validation. So in simple terms, method verification is just the process of confirming that a standardized or manufacturer's provided method performs as expected in your lab with your personnel, equipment, and environment. So it just demonstrates that the method meets the performance specifications. Sometimes we get confused between validation and verification. So maybe just to highlight, validation and verification, they're not very different, but again, we need to distinguish the two. Validation establishes that a new or modified test method is fit for intended use. And verification confirms that a standardized method performs as expected in your lab. So validation, for example, you're given, the manufacturer say this particular kit, it's going to test maybe proteins in CSF. But there's someone who is curious and says, I think the same kit can be used to test proteins in synovial fluid. Okay. Now, here, what you're going to do is validation, but not verification, because the manufacturer has not given you, or rather, given you the performance specification or directed you on what exactly to do. Okay. So, on a light note, in simple terms, the manufacturer validates the recipe and the local chef verifies they can cook it correctly in their kitchen. I hope that is loud and clear to everyone. So when and why to perform TMV? So these are some of the scenarios when we'll be required to do a test method verification on a method or a kit. We can verify a method or a kit. So number one, when a new method is inducted in a lab, you'll be required to do a test method verification, either on a new equipment or an old equipment. Number two, when the new equipment is installed also, this will be part of the performance qualifications. Okay. Number three, the established method is revised or modified by the manufacturer, e.g. the AMR, the analytical measuring range, or addition of a step, or change in the chemical, or change in a calibrator. For example, we have reagents, for example, AST. We have AST that uses, there's a method for PYP, and then there's a method without PYP. So in the case that your lab is using a method AST with PYP, and in an event that you are supplied a reagent which does not use PYP, then you'll be required to do a test method verification. Number four, when the quality control indicates that an established method is changing with time, maybe there is a constant bias, you can be able to see, maybe the bias is showing actually there's a problem in your system. So you'll be required to do a TMV. And lastly but not least, when reintroducing a test, for example, you've discontinued a test for more than 6 months. So you'll be required to do a partial verification, just a short one. But if you suspend that test for maybe more than 6 months, a year or two, then you'll be required to do a whole full test method verification to confirm that your method is stable for the past performance. Okay, so someone might be asking, why are we doing TMV? Is it even a requirement by the ISO standard? Yes, it is. The ISO 15189-2022 under clause 7.3.2 it states that laboratories must verify performance characteristics before introducing tests. This ensures confidence in results, patient safety, and reliable decision making. Remember, the ISO 15189-2022 is risk-based, and that's why we need to see that our patient's safety is a key in whatever undertakings we are doing in our lab. Also, the importance of method verification and quality assurance, that is internal quality assurance. It also establishes the baseline for performance and also supports traceability and defensible reporting. That is, if you're saying my reportable range for this particular analyte is this, where is the evidence? Where is the data supporting that? How you arrived to that, okay? So let's look at the process flow of a good test method verification study. So number one, a new equipment or test kit is received by the lab. The equipment is installed, installation qualifications done, operation qualification also done. This is done by the manufacturer or the supplier of the equipment. After that, staff will be trained. Still, after staff is trained, the next thing, a protocol is prepared by the user. Then it will be reviewed and approved by the lab head. After that, TMV study sheets are shared with the user. So the lab will begin its verification in that order. So data will be captured on daily basis. That is from precision, accuracy, and so on and so forth. And then the TMV data and report is reviewed and approved. If in the event there is any outlier or rather something that is not conforming, you'll be required to do a corrective action, and all this should be documented. And after that, once that is done, the TMV is compiled, the compilation is done, and documentation archival. Basically, that is the 7-step workflow or process flow of a TMV. So let us familiarize ourselves with the kind of study we are going to encounter, or rather we're going to discuss under this webinar. So number one, we are going to discuss precision studies. And what is precision studies? Ideally, is the assessment of repeatability and reproducibility of a test method. So under precision studies, we have intraday precision, the so-called repeatability. So the variation in results when the same sample is tested multiple times in a single day, that is what we call repeatability or intraday precision, or some even go ahead and call it within day precision because it's done within one day. Number two, we are also going to look at intraday precision, which is variation in results when the same sample is tested across different days, okay? What we call reproducibility. We're going to see why are we doing intraday and why are we doing interday, okay? Number two, we are going also to have accuracy studies, or what we call comparison studies, or the trueness, okay? So evaluation of a test method accuracy by comparing it to a reference or existing method. Number three, we look at analytical measuring range and clinical reportable range studies. So determination of the range of values that can be directly measured, that is AMR, without any dilution, without any spiking of the sort, okay? And we are going also to discuss the CRR, which is reported after sample processing. Maybe you've done some dilutions and stuff like that. Number four, we're going to look at a retention sample study, where we're going to do analysis of stored sample to evaluate result consistency over time. And this time, where do we get it from? The manufacturer's claim. We just want to confirm whatever the manufacturer is saying is true. Number five, you're going to look at the carryover study. Here we're going to do an assessment to determine if a high concentrated sample is affected by subsequent low concentrated samples. very important in instruments or other analyzers using non-disposable tips or probe, okay? And finally, we're going to look at BRI verification studies, which we're just going to confirm that the reference intervals used are appropriate for the local population. Remember, these methods are developed somewhere else in the world, and they don't serve the same population as ours. So we need to verify that the BRI that the manufacturer has stated is kind of the same before we subject it to our patients. Right, so let's begin. Precision studies. As stated earlier, this one refers to the closeness of agreement between independent test results under stipulated conditions. And as stated earlier, we have two types, the intraday precision and the interday precision. So the intraday precision, which is also called repeatability, or you can call it within day precision. So test the same sample multiple times within a single day. It identifies short-term variability. So why do we perform intraday precision? So the reason why we do an intraday precision, this one will enable us to estimate the random error or the imprecision that will be there within that short period of time, okay? So the variability that you're talking about here, it's the pipetting precision, short-term variation in temperatures, or a stability of the instrument within that short period of time. So we need to be able to demonstrate that within this short period of time, yes, we are able to meet the precision that we need, okay? Next, also something to note here, a low CV percentage in this case, of course, we're using CV to measure our precision here. So when the CV is low, this is best. What it confirms that our method is very consistent, all right? So next we have the interday precision, or what we call the intermediate precision. Some people call it between day precision. So this test the same sample across different days, right? This can be between 3 to 5 days, depending on how you've defined it in your protocol. And then what is the goal? It evaluates the variability due to time, operators, and environmental factors. Remember, you're doing it between 3 to 5 days. So different operators definitely are going to run these samples. And again, we're going to have we're going to check the fluctuations in instrument in terms of the number of days. And again, we're going to see how stable is your calibration curves within this 5 days or 3 days, okay? So we need to see. So a low CV in this case, it will demonstrate that our method is very robust and it's able to reproduce results within this particular 5 or 3 days that you've stated. So statistical methods used while estimating the precision here, we're going to use the mean, the standard deviation, which all these together, we're going to calculate our coefficient of variation. So the formula is given there. Our CV percentage is equal to the calculated as D divided by the mean multiplied by 100, okay? So acceptable CV percentage depends on the analyte and the clinical requirements. Before I move to the next slide, just to mention something very briefly. So someone might be asking, yes, I've done my precision, that is intraday and interday. If you look at the manufacturer's acceptable limits that they're giving, you will notice that the intraday precision normally it's very narrow, and then the interday precision is a little bit broader, okay? So why is it so? In the case that, yes, it has failed, you've done your intraday, your intraday has passed, then the interday has failed. And then you've checked maybe your calibration curve is active, it's good, there's no any constant or proportional error? Is it allowed to use a lab-defined CV? Someone might argue and say, yes, it's allowed. Someone might say, no, it's not. Both of them are correct. But something to note is that it is acceptable to use a lab's defined CV only when the lab defined CV is within the acceptable quality goals. And what are these? What are these that we are talking about? Here we're talking about things like the clear allowable error, percentage error, the BVD, for example, the Westgard desirable imprecision criteria, stuff like that. So if your lab defined CV is within these acceptable limits, then you can go ahead and accept that particular outlier. Okay, but something to note, do not use a lab defined CV when it's too high, because when it's too high, it means your method is not robust, your method cannot reproduce results, there's no any consistency in your method. So you're not allowed to use your lab defined CV before checking whether the bias or the errors you're getting, are they due to operator? Is it because there is poor equipment maintenance? Is it because your reagent is contaminated? Is it because of the environmental factors, maybe the temperatures, they're not controlled, stuff like that. So before you decide to use the lab's defined CV, there are things you have to check before you decide to do that. And also, in the case it has failed, as part of troubleshooting, or rather even documentation of your CAPA, you will be required to put down the reason why the manufacturer's precision claim was not met. You will be required to justify the use of your lab-defined CV with data and risk assessment done. And also, set IQC limits and monitor closely using the Westgard rules. And also, the EQA results will be monitored closely too. So these are the measures you can put in place. Yes, you have not met the manufacturer's claim, but if you have a feeling it has failed because of some other reasons except those four that you've mentioned, yes, you can accept it using your lab defined. I hope that is clear. So next, so this is an example of a precision study plan. This particular lab, they've said our experiment 1.1 precision check within day precision. This experiment is performed in 1 day. The mean SD and the CV percentage is calculated. So this is how they're going to do it. They decided they're going to do, in the morning, they're going to do 2 levels, duplicates. Remember, you can either use QC or patient samples. But if you're using patient samples, it means they need to be within near medical decision limits, okay? In the evening also, they're going to do 2 levels in duplicates. That is for intraday. So for the purpose of between day, or what we call the interday precision, they're going to run 2 levels controls twice a day, maybe morning and evening, for 3 to 5 days, and then they are going to calculate the mean SD and CV. So this is an example of a precision study plan. All right. Next, we have accuracy assessment. So accuracy is determined by replicate analysis of sample with known concentration of the analyte. So typically, they are evaluated through maybe inter-instrument or inter-lab comparisons. When I say inter-instrument, it's within the same lab. Maybe you have equipment A. Let's say, for example, you have if1-1, 2 if1-1s in your lab. So it's against if1-1 number 1 and if1-1 number 2. Okay. The inter-lab comparison, you can also do it against lab A and B, which lab A is your reference lab, you're the lab B. So 2 key aspects of accuracy that we should take home. We have number 1, the degree of agreement, that is the correlation between the 2 data sets. Number 2, the bias, or what we call the systematic error that may exist despite high correlation. Just to mention, your method can be can be having a very nice correlation factor. The R can be so perfect, but still the bias is there. So you're going to see how we're going to correct some of these biases and how to counter them. So the correlation coefficient, which is normally expressed as R, it just shows the strength of relationship between two methods. So when you have an R of -1 or an R of 0 or an R of 1, what does it mean? So we are told R ranges from -1 to +1. So what does it mean to have an R value, or rather a correlation coefficient of 0? Simply what it means is that there is no relationship that exists between the two methods. Or rather, the data points are just scattered everywhere. Your equipment is, or rather your method is doing some guesswork. So when you do your studies and your R is 0, it means there's no any relationship between the two methods. Number 2, what does it mean to have an R which is greater than 0 and equal to 1? So this one explains that there is a correlation in that it's directly proportional. It's the positive side. What simply that means is if the true glucose value in method A, or the true glucose value, is increasing, your test method shows also an increase in glucose levels. Not necessarily the same. If you're getting 5 and here you're getting 5. No, if you're getting 5 in your method A, which is the true value, you're getting 5, and your method B, you're getting 4. If it moves from 5 to 10, you're able also to move from 4 to 8. Yeah. So there is a relationship which is on the positive side. What does it mean to have a R which is less than 0? This one means that there is a correlation which is inversely proportional. It is constant, but it's backward in the opposite direction. That is, if your method A is showing an increase in glucose values, your method B is showing a decrease in glucose values, and it's constant. Okay, so a correlation of R indicates that the model explains all the variability of the response data around the mean. It's fully accurate. So for methods to be considered comparable, your R should be greater than 0.975 and your R squared should be greater than 0.95. All right. So how do we assess correlation and identify errors during our test method verifications? We normally use the linear regression analysis. This is the only module that we can use to quantify our errors and know what kind of errors we are facing and how to deal with them. So we have two common culprits here, which is the constant error, which the constant error we get it from the intercept deviation, the y-intercept deviation. And then we have the proportional error, which we get it from the slope, the gradient. We are going to look at this just right now. So I want us to look at our example here. I hope you can see. There is this line here of best fit. I don't know if it's green or blue. When you look at that data provided there, if you try to analyze, you'll realize your y-intercept, it's 0. Yes. And most of the data points are within this line, the line of best fit. So in this case, from the equation y is equals to 0.947x plus 0.2311. Our y-intercept in this case is 0.23, which is very close to 0. This is very much okay. Our gradient is 0.9. which is also okay. But there are two lines. You can see there is this red one and the yellow one. So I'll start with the red one. If you look at the red line, the y-intercept is something close to 100. What does that mean? This is what we call a constant error. And what is a constant error? And briefly, I'll just discuss about it. We can find time maybe in another platform and talk more about these errors. But just on a snapshot, so the goal for any test method verification is that your intercept should always be zero or very close to zero. So it is very possible to have an R, or rather the coefficient of variation, which is 1, but still have a constant error. Yeah? What it means is there is a constant difference between the two methods. If you look at this red line, when the intercept is 100, it means that if I'm getting, maybe I'm doing a TMV for something like maybe cholinesterase, the actual value is maybe 6,000. But when I do it with my method that I'm trying to verify, I'm getting 6,100. Okay? So there is a constant error. So how do we go about it? How do we go about it? And what causes a constant error? So let me begin by that. What causes constant error? Number one is maybe inaccurate blank measurements. It can lead to constant errors. Number two, contaminated reagents. They can also lead to constant errors. And number three, incorrect calibrations can also lead to constant errors. So what do we do when we realize our method is giving us a constant error? What you can do, you can just try to recalibrate the method to get a new curve and repeat and see. And in most cases, it will just recover properly. Given that you're living in a world of limited resources, maybe you don't have that calibrator. What else can you do? You can use a correction factor, but this is a short-term thing. You are not going to use it for long. You have to recalibrate. But you can use a corrective factor. For example, if you realize the constant error is giving you your y-intercept is 100, definitely when you do your measurements, you can just subtract the 100 and get the actual value that you need. I hope that is clear. And then there's another culprit called proportional error or the slope deviation. I want us to look at the yellow line. If you look at this yellow line, there is no constant error because the y-intercept is something very close to zero. But as we move further, it's moving away from the real true value that we want to achieve. So proportional error means that the error increases or decreases with the size of measurement. So if the slope is not 1, the new method it's either overestimating or underestimating the results of the values. Okay. So this type of error is not constant. It might either get worse as the value increases, or it might get better when the values also go higher. So in this case, if you try and look at the slope, you'll realize maybe changing y over changing x is giving us something like 0.5. So what it means is that 50% of the results you're getting, you'll be required to multiply them by 0.5. Yeah. So what causes a proportional error? Again, incorrect standard. Number two, these are just examples, wavelength interferences, and also incomplete reactions, especially at high concentrations. You realize some analytes, some methods cannot really quantify a given analyte at a given point when the concentration is high. So these are some of the reasons that can lead to a proportional error. So what do we do in this case? Again, you'll be required to recalibrate. Of course, you can use a corrective factor, but this is not long term. The best way is just recalibrate, and in most cases, for a good method, is going to recover. I hope that is very clear. So this is an example of an accuracy study. So in this lab, they're doing inter-lab comparison or inter-instrument comparison. So samples will be processed in the existing equipment, or the reference lab will be processed in an instrument under verification in the lab. Results will be compared. Samples should preferably cover the linearity range, and then the bias percentage, coefficient of correlation, and R squared will be calculated, and the blood Alsman graph will be plotted. So the R squared will be reviewed only for sample size either 20 or above 20. So if you have a sample size which is less than 20, definitely you're not going to get the R squared. All right. Still on accuracy, something maybe I should mention. Someone may ask, is it possible to do comparison between methods that are not, or rather different methods? For example, I want to do a method verification of HbA1c, and in my lab, I'm using the Biorad D10, but my reference lab is using maybe Cobas. You see, these are two different methods. With Biorad, I'm using HPLC, and maybe Cobas, it's using turbidimetry. Is it okay for me to do comparison between these two different methods? Yes, it's very possible. It's very possible, but there's something to note. Under the guidelines provided by EP09, the CLSI, so the purpose for accuracy studies is to estimate the systematic difference, that is the bias, determine the interchangeability between methods, and ensure that the new method gives clinically acceptable results. Yes, you can compare between two different methods, but something to note, or a risk that might arise when you're comparing methods that are different, is that different methods may react differently to interferences. Maybe my biorad is not affected by hemolysis, but maybe Roche, it is affected by hemolysis. And many others. Number two, also, the bias may be intrinsic due to the method design. That is, the bias is not due to the random error or sample-specific issues, but rather due to fundamental difference in how each method is designed or it's operated. So yes, you can do comparison between two different methods, but you should note the two things, like difference in interferences, and also the bias may be too intrinsic. Well, next we have retained sample studies. By definition, a retained sample study evaluates whether, I might need to rush a little bit, okay. A retained sample study evaluates whether stored or archived sample provide consistent results over time. So the study is performed to verify manufacturer's claim of stability for a given analyte when stored as per manufacturer's instruction. So the study is performed to verify manufacturer's claim of stability for a given analyte. So this is the approach. Retest the stored sample at defined intervals. Then you'll use acceptance criteria. In this case, you'll calculate the bias, compare the results against the manufacturer's claims, any national or international reference like the CLAI and stuff like that. There's nothing much. This is an example of a protocol example. I won't read too much through it, but this is one that you can have in your protocol. Next, we have the carryover studies. So carryover refers to contamination or influence of high concentration sample on the result of the subsequent low concentration sample. So the purpose is to ensure that the test results are not affected by the previously analyzed samples. So it applies only, underline that, only, if you're using automated pipettes where the probe tips are not disposable. So to be determined, you can use at least 2 parameters. You don't need to do everything. 2 parameters are enough. So the study design, alternate high and low samples, either high, high, then low, low. So analyze whether the low samples following a high sample shows elevated results. The carryover is expressed as a K, and that is the formula that we use to calculate it. Once you get your result, we will need it to be at least or equal to 1% of the high sample value. For a low sample followed by a high sample, it's not statistically significant, so you might not really be interested in that. The only interest is when you're running a high sample followed by a low sample. Next, we have BRI, what you call biological reference interval verification study. So the BRI verification ensures that the reference intervals used by the lab are appropriate for the local patient population. So the purpose is to validate the applicability of the published or manufacturer's provided reference intervals. So something to note is that most significant flaw that we normally forget is that the manufacturer's BRI is not representation of your patient population. So you'll be required to perform a transferability study. That is, you'll be required to confirm that, yes, the manufacturer is saying between this and this is the normal, between this and this is pathological, then you'll be required to do it. And this is the study design: collect data from a minimum of 20 healthy individuals, compare the results against the stated reference intervals. So the acceptance criteria is that no more than 2 out of 20 results should fall outside the reference range. If more, the lab must establish its own BRI through a formal reference interval study. And this is, if it fails, then you are required to do a robust one, which you will definitely use around 120 or more samples of healthy individuals, come up with an inclusion criteria, maybe individuals who are not taking medicine, stuff like that. Also the age, the gender, the race, things like that. In the case you've done your 20 runs and they have failed. Next, we have the AMR. So the AMR, or the analytical measuring range, is the range of an analyte concentration that a method can measure directly without sample dilution, concentration, or any pretreatment. So to define the upper and the lower limits at which a method provides accurate and precise results and under routine conditions. That is the purpose of doing AMR studies. So you will get your bias and your CV. Next, we have the CRR, the clinical reportable range. This is broad-based. So the results that can be reported after any necessary sample manipulation, for example, dilution, concentration. So the goal of this is to determine how far test results can be extended and still be reliably reported to clinicians. So So this one confirms that the results remain valid after sample dilution or concentration. Okay. So AMR is a subset of CRR, as we've seen. So CRR includes both directly measured and processed results ranges. So this is also an example of it. I won't read through it because of time, but this is one of the examples that you can use in your study design. So my reference, these are my reference. Of course, our ISO 15189 2022 is our Bible, I would say. Okay. Yeah. And that brings me to the end of my presentation for today. And I take it back to you, my moderator.
Yeah, thank you so much, Mr. Dennis, for giving us a wonderful presentation. And so without wasting time, we will move straight to our area for questions and answers so that we are able to have a discussion on the questions that we have. So our first question comes from Ngeno Peter, and he is asking a question here, and it goes, how would you design and statistically justify a quantitative test method verification plan for a high complexity laboratory assay, ensuring compliance with ISO 15189 of 1022 and CLSI EP 15A3 guidelines, while accounting for accuracy, precision, detection limits, and matrix effects in your specific laboratory setting? Danish, are you able to give a response to this question from Ngen or Peter?
Yes, it's a very broad, it requires a very broad answer. And I don't know
Mhm.
if I'll exhaust everything. So ideally, the first thing you need to come up with a study protocol, a protocol. And how do you design your protocol? Majorly, you need to tell us, number one, you need to tell us how are you going to conduct your precision and what are your acceptable criteria that you're going to use, and you need to specify in your protocol. Number two, you're going to tell us how you're going to perform your accuracy studies, or rather the trueness, and what are your acceptable criteria for this matter. Number three, it's the whole of this thing that we've been discussing. We need to see in your protocol that you've stated, this is how you're going to do your precision, and this is the goal that you're looking for, what is your acceptance criteria. So after all this, precision, accuracy, what else did we talk about? Let me just take you back there. Ideally, this is a very broad question, and I think if we let me just take you back here. Yes. So from the process flow that we are discussing before, a new equipment has come or a new test method has been introduced, you've trained your staff, you develop a protocol. The protocol will define everything for you that you're going to use to do, from precision up to the BRI verification. So I don't know if I'm answering you satisfactory, but it's a whole, you know, it's a broad-based answer. So the protocol will guide you in everything, because the protocol will state what are you doing and when are you doing and why are you doing and what are you evaluating against and what is the goal. Yeah, in simple terms, that's how I will respond to that.
Okay, thank you. Let's look at another question from Samuel Itatu, and he says, is there a software to calculate R, or I have to use a paper and a pen?
Yeah, very nice, very nice. Yes, there is a software, especially if you are dealing with, you can imagine a lab processing over 130 over 100 analytes and doing the mathematics manually. It's tedious. There is a software that can do all these things for you. It can calculate for you the R, it can calculate for you the R squared. Yes, there is a software for that.
Yeah, thank you, thank you. Let me check for another question. Yeah, we're looking at our next question here. And here, yeah, we also have a number of participants who are requesting for the slide. Mr. Dennis, you can also respond on that. Are you able to share the slide that you used for the presentation? So a number of are asking.
Mhm. No problem. I will just share them. This is for our consumption. Definitely, I will share the slides.
Thank you. Another question from Michael Ongoro.
Yes.
From Michael Ongoro, and it goes, what does it take to become a certified internal auditor?
That is out of
A good
context.
question there. Yeah, that's a good question.
Yeah, it's a good question. Yes. So what it
Yeah.
takes is, I'll just mention briefly. First is the training. You'll be trained. There are companies who are training people on internal audits and risk assessment. So after the training, there's an assessment that you'll do. There's an exam you do. Once you pass the exam, you become certified. And then, of course, you need to practice. You need to practice.
Thank you. Another question from Victor Kibet,
Mhm.
and it goes, how do we calculate clinical decision limits?
Clinical decision limits.
Yes.
I will I will give an example. Now I'll give an example. Let's look at something like, let me just pick one analyte, the obvious one, maybe glucose. Maybe glucose. So
And Danish, just a minute.
yes.
As
Mhm,
you plan to answer that, we also have Florence Onyango,
mhm,
who seems to have a point to make. So as
mhm.
you answer that, maybe I'll inform Florence Onyango to be ready to maybe talk, because I'm going to put her mic on.
Okay.
Continue. Yes.
Should we let her talk first and then I respond to the question?
Um.
Because I'll take
Let
some
me
time.
see.
Yeah, just let her talk.
You can continue as we let her talk.
I can continue?
Yes. Yes. Kindly.
All right. So, clinical decision limits, the guidelines are, you need to, one important thing that you need to know, all these things, they have to be evidence-based, clinical guidelines that guides us on uh, how we arrive to this particular thing. So I'd say, so in most common robust approach or clinical designs, there are studies which are done, and most of us we get them from IFCC. For example, in the case of maybe HbA1c, we by the guideline, a guideline for managing diabetes might set a specific HbA1c value, e.g., maybe say greater than 6.5% is a diagnostic threshold based on the clinical evidence. That can be one way of sourcing or rather arriving to your clinical decision limit. Number two, you can get all this from the biological variation. So this one focuses mostly on the natural fluctuations of an analyte within an individual between different times. So it's used to determine how much a result must change to be considered clinically significant rather than just a random variation. Okay, so I don't know if you've heard things to do with the RCV, the reference change value. So with the reference change value, the minimum change in a patient results over time that is considered statistically and clinically significant is calculated there's a formula for that. So I don't know if we we can have another session for this, but yes, the biological variation can be used also can also help us to arrive to our clinical decision limit. So we can have the broad-based, that is evidence-based medicine and clinical guidance, for example, the IFCC, and also we can have the biological variation, okay? Things like that. I hope he's answered.
Yeah, thank you. I think Florence Onyango is on. Florence, if you can hear us, you can unmute your mic and speak. Florence, are you able to unmute your mic so that you speak? I think we'll get hold of her when she's ready.
Okay.
Meanwhile, we can proceed, and we want to tackle another question. And we're getting a question. We're also urging our participants to check for these slides in our YouTube channel. That is Lab Medicine Society of Kenya, and also our Learning Hub. We are able to have these videos there, so you can visit so that you're able to learn. Another question from Justin Kipchumba, and it goes, does accuracy and precision have correlation?
Does accuracy and precision have correlation? That's
Yes.
a very, very nice question. I would go back to our definition to make it easy for us, okay? So by definition, precision is the assessment of repeatability and reproducibility, while accuracy, it evaluates the test method accuracy by comparing it to a reference or existing method, okay? Under precision, what we are interested in is we are looking at our method. Is it able to reproduce the result? Is it able to, within a short period of time, is it able to repeat whatever it has done? That is the goal of precision. But accuracy, what we are trying to arrive at is we are now doing the comparison. If my method B, method A is the reference. If method A is saying I'm able to quantify this analyte glucose and I'm getting 6.5 millimoles per liter, and my method which I'm verifying, it's giving me something like 6.4, then I would say there is some relationship and my method is accurate, okay? But now in precision, what you are interested in is the no matter how bad or rather how far it can be as compared to the reference method, but it's able to reproduce whatever. If it gave me maybe 7, if I do another run, it's giving me 7.1, 7.2. You see, the CV is very narrow. It's very narrow. It means, yes, my method is very precise. So your method can be very precise, but the accuracy can be poor. At the same time, your method can be accurate, but the precision is poor. So they are kind of related, but it doesn't mean all of them. Well, ideal one should be precision and accuracy should be perfect, but there are some cases when precision is good, accuracy is bad. Accuracy is good, precision is bad. I hope that is clear.
Thank you. William Musyoki is asking, he is saying, thank you, Baraza, for the great presentation. I hope there will be a part 2 for this so that measurement uncertainty will also be tackled. It's an important aspect as well and very useful
Yes.
for useful
Yes.
data for clinicians. That is right.
Yes.
Thank you, William. So another question from Daniel Wekesa, and
Yes.
he starts by saying, thanks, Dennis, for the presentation. And so the question he goes, how do you determine healthy individuals for the reference ranges?
The inclusion. Okay. Okay. I will I will use a simple example. For example, in your lab, if you want to establish maybe well, it's not the same thing really, related, but I'm just trying to borrow the same idea. MNPT, okay? How do you arrive at your MNPT in your lab? Mostly you pick, there are individuals who are healthy. Like you're not under any medication. That will be the criteria number one. You're not under any medication. In the last like 3 months, you've not been hospitalized. Okay. You don't have any underlying condition. Okay. You are, for example, if I'm saying I want to arrive at a BRI for HB1C for, no, not HB1C. Let's say what? Um, which is a good example. The HB for kids. Definitely the HB for kids will not be the same as an elderly person. So my inclusion criteria, if I want to get the BRI for kids or the PIDs, again, I will go for maybe patient or rather individuals who are healthy between the age of 1 and 5. Okay, something like that. So the idea of healthy individuals, you have your inclusion criteria for your study. That is, this person is not having any underlying condition. They have not been hospitalized maybe in the last 2 months. Okay, they are not on any medication or stimulants or stuff like that. Yes.
Yeah, thank you. We're getting another question from David Wamalwa, and it goes, what are the factors affecting accuracy?
Factors affecting accuracy. Yeah, very good. Yes, factors affecting accuracy. As we were discussing, we mentioned something about a constant error and a proportional error. Okay. And we said a constant error can occur when you're doing your calibrations, you didn't do them correctly. Yeah, incorrect standard. Maybe you're having an issue with your wavelength. For the spectrophotometric analytes, maybe issues with your reagent, yeah, contaminations, stuff like that can affect your accuracy studies.
Thank you. Thank you. Another question from Paul Odongo, and it goes, "Hello, Mr. Dennis. Most of analysts are manufactured outside our population. Is it right to generate our own biological reference to suit our population?"
Yes, yes. Actually, when you're doing a BRI, as you look at the model, remember I said there's a rationale that I began with a statement saying most significant flaw is that manufacturer's BRI is not representative of your patient population. So you will be required to do your verification for BRI. That is, you're going to use 20 samples, okay? So so out of the 20 samples, if all of them fall or 19 of them fall within the range that you've manufacturer is claiming, you can go ahead and use the manufacturers. But if more than two fall outside, then you will reject the manufacturer's reference interval and perform a formal reference interval study. And here you'll be required, it's going to be very robust. You're going to use at least 120 samples of healthy individuals to establish your new reference interval tailored to your population. I hope that is clear.
Thank you. We also have a participant who wants to say something. Smith Oyo, are you able to hear me so that you can unmute your mic and give us your point? You seem to be having a point to give us. You've raised your hand. Smith Oyo, are you? Yes, yes. Talk to us. Smith Oyo, we can't hear you. I think we can proceed. He has unmuted, but we are not able to hear what he is saying. We can proceed as we plan to wind up. Now we have another question from Jack Muthi, and it goes, does these studies apply in other clinical areas such as microbiology, histology, parasitology, hematology? Putting into consideration clinical chemistry takes a high percentage of these data studies. Back to you, Baraza.
Yes. Our topic today was quantitative test method verification. There is also qualitative test method verification, whose protocol is kinda different, okay, but almost the same things. But again, hematology still falls under quantitative test method verification. You'll be required to do retained samples, you'll be required to do AMR studies, you'll be required to do CRR studies, yeah. But when it comes to something like parasitology, it might be a little bit different. There you might be forced to do a qualitative test method verification, yeah. Histology might be required to do a qualitative test method verification. So our today's, maybe we'll have another forum where we'll be discussing qualitative test method verification. But our discussion today, mostly, I think the most area that are affected by this is clinical chemistry, hematology. Yes. Yeah.
Thank you. Kenneth Wanyonyi seems to be having a point to put across. Kenneth, if you're there, you can unmute and talk to us. Kenneth Wanyonyi, if you are there, you can unmute your mic and talk to us. As we wait for his response, we can look at another question. From a question from Douglas Okwako, and it goes, what's the difference between method verification and method comparison? And using the sample, can I use verification data to do method comparison?
Method verification or method comparison. All right. Uh, Remember, at some point I mentioned that I actually raised the question and answered it myself when I asked that, is it acceptable to do comparison with a reference method or a different method? Okay. So when you're doing method comparison, method verification, you will be required, if you're using, if the method you're using is maybe turbidimetry, you're trying to verify turbidimetry, you'll also verify it against turbidimetry. But if you're using turbidimetry and you want to compare it to, let's say, something like HPLC, this would be method comparison. The guidelines give us a leeway that, yes, you can be able to do that under the CLSI EPO A3, because what is the goal of, what is the goal? The goal is to estimate the systematic difference, define the interchangeability between the methods, and ensure that the new method gives clinically acceptable results. But again, there is a risk for this. When you're confusing test method verification and test method comparison, when you're comparing between two different methods, and I mentioned that different methods may react differently to interferences, and also the bias you might be getting in that particular method may be so intrinsic in the sense that the method design maybe in HPLC, the specifications are actually uh, fundamentally different in how each method is designed. HPLC is definitely different from turbidimetry. The second part of the question, can I use verification data to do method comparison? I would say, why would you use that? Because the idea is, if you have the data that you've used to do your verification with, and you're comparing it against a different method, yes, you can do it. You can do it. You're given a leeway to do that. It's in the guidelines. But the risk is there, that you should know that the different method may react differently to interferences, and the bias also might be very intrinsic. Yeah.
Thank you. Now to our participants, just a reminder, you can join our WhatsApp. The link is under the chat box. You can join by clicking that link that I've shared. You can also access our YouTube through the YouTube link that I've also shared, our Facebook page as well through the link, and our WhatsApp channel as well from the link that I have shared. You can check all these under our chat box. And then we have our last question from Mr. Justus Mutinda Kingwa, and it goes, is this topic related to Levy-Jennings chart? Next time, we can have a presentation on how to interpret Levy-Jennings rules. Now, a question to our presenter today, maybe is this topic related to Levy-Jennings chart? You can give your response on that, Baraza.
Well, no, it's not related to LJ charts. The major thing here, we are trying to look at the method verification. We're just trying to justify, or rather, justify that the performance of our new method is conforming to what the manufacturer is claiming. That's it. LJ is a totally different thing.
Okay, good. I think we have exhausted all the questions, and we are at liberty to. There's another question that has popped in right as we were ending this session, but let me go through it. It's from Paul Odongo, and it goes, he says it's a wonderful presentation. And then the question is, what is the accepted margin error in quantitative verification?
What is the acceptance margin error? Well, all these things are given in the CLIA allowable error. Okay, and some of them we will get them from things like biological variation, BVD, the Westgard desirable imprecision criteria, and stuff like that. And when you're designing your protocol, these are the things that you're going to capture. Remember, I said there's somewhere you're going to tell us, this is going to be my acceptance criteria for these precision studies. This is going to be my acceptance criteria for my accuracy studies, because all in all, the, the the reason why we are doing all these studies, we are trying to estimate the total allowable error. And how do we arrive at total allowable error? It's the summation of the random error. And where do we get the random error? The random error, we get it from the precision studies added to the systematic error. Where do we get the systematic error? We get the systematic error from the accuracy studies. So all in all this, the total allowable error, there are guidelines that are given. So from whatever you get, subject it to your acceptance criteria, and you'll be able to know whether your method has passed or it has failed. Thank you.
Thank you, Dennis. We have now come to an end of our today's webinar, and so I will wish to allow Dennis to give his parting shot as we close this presentation. Welcome again, Dennis.
Yeah. Team, thank you so much. It has been a pleasure to interact with you guys. And we are looking for, I've seen comments on when is the, can you plan for another webinar on the maybe qualitative test method verification, measurement, uncertainty. And maybe my colleague here will do something about it. But all in all, I thank you all. Thank you for your participation. Really appreciated. Thank you. God bless you.
Yes, thank you, our presenter, and also thank you, our participants, for finding time to be part of this presentation. As we are planning to do another webinar on Wednesday, we welcome you all so that you may come and we learn together. Otherwise, from where I sit on behalf of Lab Medicine Society of Kenya, we thank you all and we appreciate your efforts and your dedication to always attend our webinar. My name is Zathay Mari, the Secretary General of Lab Medicine, and I wish you a good evening as we plan to meet on Wednesday. See you and thank you.
Thank you.